Right, let's continue. I kind of preempted this slide a little bit when I started talking about costs earlier on, but may as well take another look at it because it's important for a lot of the rest of what we're doing. Okay, so I want to see if we can work out, given a table, given a query, how much is it going to cost to answer that query. Two ways you could think about that, and they're clearly related to some extent, is to work out the total time cost. The other possibility is to work out the cost in terms of the amount of I/O that you have to do. So the basic assumption that we're making in all of this stuff is that doing anything in memory costs virtually nothing, and doing stuff that involves reading and writing costs a very large amount. So we want to make sure that we minimise the amount of reading and writing we do. Now, either of those measures isn't ideal. Time cost is certainly not ideal because you run it on a different machine with a different disk and you'll get a different time. And if you're using SSD, you get totally different time again. And also it can be affected by the current load on the machine. So if you've got other people accessing the machine at the same time, that's going to affect that as well. So it's not that useful to talk about the total time. So I'd say that if we want to try and compare two different join methods to try and work out under what circumstances one is better than the other, looking at the page cost might be better, because it identifies the workload that the method is going to impose on the database engine. But once again, a problem with that, it depends who's accessing the database at the moment and what kind of queries they're doing and how that affects what's in the buffer. So trying to estimate costs accurately and take into account what's happening with buffering is almost impossible. So basically what we're going to assume is that every time we ask to access a page to read it, we do a read operation. When we want to write a page, we do a write. So essentially we're assuming no buffering at all. Okay. Right, so these quantities that I've talked about briefly before, so a relation contains R tuples, so always are interested in doing things in terms of the size of objects in the system. So a relation can have R tuples, and each tuple has an average size of capital R. Tuples are stored in that many pages, each page is that size, and given the average size of a tuple and the size of a disk page, we can work out the capacity of that page. So the average number of tuples that we could store in that page. And of course we need to take into account the size of it, the directory and the size of the header and all that kind of stuff as well. If we've got a query, then the results for that query might all be located on one page, or they might be spread across a number of pages. So to try and capture that idea, we've got this B sub Q, which is the number of pages that contain answers for a particular query, Q. Data is always transferred between disk and memory in whole page chunks, and in Postgres we know that that's 8K, and the cost of this transfer is very high. But as I said, we're not going to take account of cost of time when we're calculating cost anyway, except maybe once. So what's a relation look like? Basically a sequence of B blocks where each block contains some number of tuples, up to C tuples. So all these cost models are a little bit rough, but they do give a feel, especially at the level of order N type complexity feeling, for how expensive the operations are. And here's a nice example that I pinched from Alan Feckney at Sydney Uni about how rough estimation can actually sometimes produce reasonably accurate results. So the question is, how many piano tuners are there in Sydney? And to some extent what we're actually answering, how many piano tuners does Sydney need? Alright, so Sydney's got about 4 million people, that's probably more by now, I don't know. Average household size is about 3, therefore there are that many households. Let's make an assumption that only 1 in 10 households has a piano, and then we'd have 130,000 households with a piano, so that's 130,000 pianos. That's assuming they don't have 2 or 3 pianos, which is unlikely. Alright, so if people get their piano tuned every couple of years, then the number of pianos that need to be tuned each year is going to be roughly half that. And let's say a piano tuner can tune 2 pianos a day. That sounds like a slight underestimate, but there you go. And there are 250 working days in a year. So 1 tuner can tune 500 pianos a year. So if 65,000 pianos need to be tuned each year, and we've got, if you like, 500 piano tuner hours available, then that's going to require about 130 piano tuners. Now, if you want to try and check whether that's a useful estimate, you look up the yellow pages for piano tuners, and that's the number of piano tuners. So it's not actually too far off, even with all those assumptions that we've made. So that's the kind of thing that we're doing in this cost estimation. All right, well, one important thing that we deal with is different kinds of queries. So it's not just a select operation. It can be important to know whether the select operation produces just a single answer or whether it can produce multiple answers. So we've got all these different variations on queries. So one kind of query is just to scan the whole table. That's fine. Another kind of operation is projection. Another kind of operation is sort. Another kind of operation is a selection, where we've got just a single attribute involved, and I'm going to call that a one-type operation. And a different kind of selection is where you can selection on a secondary key. You can have multiple tuples that match the condition. And finally, join, and there'll be various flavours of join that we'll be considering as well. So that when we're dealing with files, like we've seen, we always deal with pages, and within pages we've got tuples, and within tuples we've got attributes, and often one of these attributes is a key, and that generally turns out to be the critical attribute. So often I'm just going to write the tuples by giving their key value. Certainly in the analyses I'm going to do for the rest of the day. So here we've got a page, and obviously this isn't a real page because it's only got 6 tuples in. The first tuple has a key value of 1, second tuple has a key value of 4, and so on and so on. Right, so let's look at 3 kinds of file structures that we might deal with. A heap file is basically an unordered file where we just stack records into the pages as they arrive. A sorted file requires us to maintain the tuples in order on the key value, and a hash file uses the key value to place the tuples in an appropriate page. It's possible that some records on a page might be marked as no longer existing, and we see with Postgres that we have that kind of facility as well. Alright, so what we want to do is take a look at, I don't want to look at all the different operations. Let's take a look at, say, insertion. And in fact, there's some examples here. So if we've got a heap file, insertion is dead easy. We just stick it in the next available slot, and if we don't particularly care about garbage building up within the pages, so when we delete a tuple, it just gets marked as no longer in use. We can let the vacuum handle that. But insertion is really simple, as long as somewhere in the file we maintain an indication of where's the next available slot. So you can even just have where's the next page that's got free space. So as soon as we try to do an insertion, we look at that value, the next page with available free space is number 3. We read in page 3 and we stick the tuple into one of the slots in that page. Deletion, however, is a little bit trickier. It's going to have quite a different cost. So in theory, this is insertion is an order 1 operation, because you know where the next available space is, you go to that space and you add the tuple. So in theory, what's happening is we're reading in the page with available space, we're making changes to its internal contents, and then we're writing it out again. So that does the insertion. But it's always going to be go to one page, read it in, write it out. So that's order 1. If we're doing deletion, then we've got to find the tuple to be deleted, and this file gives us absolutely no help about where that tuple might be. So the only way we can delete a tuple is to start at the front of the file, read the first page. Is the tuple we want to delete there? No, it's not. Read the second page. Well, yes, it is. So then we mark that tuple as having been deleted, and we write that page out. So the best case is that we find the tuple that we want to delete in the first page. So once again, that's going to be one page read, make some changes to the page internally, and then write it out again. The worst case is that the tuple we want to delete, let's say it was k equals 5, is in the last page. So the only way we can find that tuple is to read all of the pages up to that page. So that's going to cost us B page reads to get to find the tuple, and then one page write, having made the changes to the page containing the tuple that we want to delete. So the worst case is pretty bad. In this case, it's always one read, one write, and we're done. Alright, if we've got a sorted file, then insertion is no longer as simple as it was, because we've now got to find an appropriate page to insert the tuple. So first thing we're going to have to do, where is the appropriate page? Luckily, the file is sorted, so we can use a binary search. In this case, one thing that would be useful to have stored in the page header, for example, is the minimum key value and the maximum key value on the page. So then that makes it, we don't have to look at the tuples in the page, we've just got to look at the min and max key value, and we know whether the thing we're inserting belongs in that page or not, or whether it's higher than that or lower than that for a binary search. So we can eventually find the page that we need to insert it, so it belongs in here. We can take that page, make changes to it, but let's say, you know, if this page has free space, that's fine. We can stick k equals 8 into it. But if it doesn't have free space, then we have this sort of cascading effect where we need to take a tuple out of this page, push it into the next page before we can insert k equals 8 into there. And then if this page was full, we'll need to take something out and push it further up. So insertion in this case can be quite complicated and relatively expensive. So finding the place to insert the tuple is log 2, binary search, and then how much it costs, how much writing we have to do depends how far along the file we are and whether there's actually free space somewhere. So, you know, if there happened to have been an empty, deleted tuple here, then we could put k equals 8, we could push k equals 9 up, and there'd be space for it in this page. So we wouldn't necessarily have to read all the way to the end. It just so happened that a lot of these pages were already full. Alright, so what about a hash file? So we're using the key as a hash, and since we've got 3 pages, we'll take mod 3 as our hash function. Very simple hash function. Alright, so if we want to insert k equals 15, 15 mod 3 is hopefully 0, and now we have a different kind of problem that arises. K equals 15 has to go into data page 0, but data page 0 has no space. It's k equals 15 still has to be associated with data page 0, but if we can't put it in the page itself, then what we can do is make another page that's associated with data page 0, and typically we'd have some kind of overflow file so we can allocate extra pages in the overflow file. So we'd have this page here, and we'd say that's full, can't fit k equals 15, make a new page in the overflow file, and then store k equals 15 in there. And the other thing we need to do is link that page there. So that's, in this case, there's going to be another thing that we need in the header, is a link to any overflow pages. And of course it's possible that these, you might end up with chains of overflow pages, because you put k equals 15 in here, and then you get 3, 6, 9, 12, then 18, 21, 24, 21, 24, and then you get 27. So this page was filled up by 18, 21, and 24. You need to insert 27. It has a hash value of 0, so it needs to be associated with page 0. Doesn't fit in there, doesn't fit in there. Add another page in the overflow file and link those 2 pages together. Ideally, you want those overflow chains to be very short, and to some extent that depends on the hash function, it depends on the number of primary pages. If you have something ridiculously small like 3 pages in your hash file, then and you want to insert 10,000 records, then clearly each of the primary pages is going to be associated with a lot of overflow pages. So how to deal with that, we'll talk about that later. Inserting, similarly we have the same problem with k equals 14. If we wanted to insert oops, that's not a very good hash function, is it? Because it's basically locked out this page here. So nothing with any key value is going to hash to that page. So that was a poor choice of hash function. So if I made it k mod 4 and eventually something came along that had a hash value of 3, then this page here is not full, so I can add something in. And the same deal would have happened here as well. If this hadn't been full, then we could have just put the tuple k equals 15 in here, and we wouldn't need to add an overflow page. I have to go back and redo the entire diagram. Oh no. Oh no. Or I can just pretend that page didn't exist. That would be the easiest thing to do. Okay, so that's an idea of how an operation like insert can end up having quite different performance depending on the file structure that we're dealing with. Right, going back to scanning, which we seem to have looked at a few times, but one more time, and this time do a cost analysis on it. So for each page in the relation and for each tuple in each page, so we assume that we're creating a result table as well. Whether that table exists in memory or whether it's written to a file. If it's written to a file, that's going to cost. I think I'm assuming a lot of the time that we don't care about the cost of writing the final result set. Okay, because if we're comparing two different methods for implementing the same query, they're both going to produce the same size result set. So it doesn't matter. However, intermediate results are very important. The size of intermediate results is very important. Potentially they have to be written to disk, and that costs a lot. If the intermediate results are large, if the intermediate results are small, then that makes things a lot cheaper. So I think this is the last time we're going to consider time cost. Basically the page cost for scanning a relation is we have to read every page. So we've got no filters involved here. We just read from the start of the file to the end of the file. What do we do if the file's got overflow pages? And this would apply whether we're dealing with a hash file or a sorted file or a heap file. So we always have to read all the pages. If we're dealing with a file that has overflow pages, then depending on what order we want things to come out, then we might read this page, then read this page, then follow this link, read this page, follow that link to this page, then read this page, then this page, and so on until we've read all the pages in the file. Remember, this is just a scan with no filter. So this is algorithmically what's going to happen for each page in the relation T, for each tuple in that primary page. I'll often talk about primary pages and overflow pages. So we read all the tuples in the primary page, and then if there's an overflow page or a chain of overflow pages, then we scan through them, and we do for each tuple in each of those pages, and we add it to the result set. So what's the cost of doing that? It's the cost of reading the primary pages plus the cost of reading all of the overflow pages. Right, what if we've got a query which does have a condition? And in this case we're talking about one of these queries that I've called a one-type query, where there's only a single result tuple, guaranteed, because we're doing a filter on a primary key. We're looking for a particular primary key value. Right, in an unordered file, all we can do is start from the start of the file and go until we actually find the tuple that we need. So we know that there's only going to be one answer, so clearly once we found the tuple, we don't have to keep reading, we can stop the scan at that point. So how much is that going to cost? Well, that's effectively what we have to do, and you know, it doesn't always have to be this condition. Clearly the scan operator is going to contain some information that represents the condition, and we apply that condition here rather than this specific one. So how much does it cost? Best case is we get lucky and we ask for an ID that happens to be in one of these tuples. Doesn't matter which one, it's still going to be one page read. The worst case is the tuple we're looking for is in the last page, or we ask for an ID that doesn't exist in the database. In either of those two cases, we read every data page. And the average case, well, we'll read half the pages. So we could characterize the cost for this kind of scanning like that. it would change if it wasn't a primary key that we were scanning for. So if we select staff from employees where name equals John, there may be many Johns in the database. So the cost then would be that we'd always have to scan the entire set of pages, because we don't know, when we find one John, we don't know that there's not another John further on in the database. Right, so what about if we're trying to search in a hash file, how much is that going to cost? Alright, well, how much it's going to cost depends to some extent on the number of overflow pages. And I keep changing the diagram structure for these anyway. So here's a hash function that actually works given the number of pages we've got. There are no wasted pages in this data file. So imagine that we ask this query where k equals 51. Right, well, one thing we can do, given that this is the hash key, then we could just apply the hash function to this value that we're searching for, and we know for sure that if there is a tuple with k equals 51 anywhere in the database, it's going to be in page 1 or in one of page 1's overflow pages. So we apply the hash function here, that gives us 1, and we look in here, is there a tuple with k equals 51? No, there's not. Then we have to look in the overflow pages, and in theory might have to go all the way to the end of the overflow chain just to make sure that it's not sitting there. In this case we get lucky and we find k equals 51 in the first overflow page. So the minimum cost is going to be a single page read. Let's say we ask for k equals 21, then the hash function would still give us 1. We go here and we find k equals 21 straight away. The maximum cost would be if we happen to hash to the page that has the longest overflow chain and the tuple that we're looking for is at the end of that overflow chain. And the average cost, minimum, maximum, right, that's all we've considered, but if you want to come up with some kind of average cost, it's going to be 1 plus the average overflow chain length. Right, here's another operation that you might say, why do we ever do this? Well, occasionally we do. Creating a relation from another relation. So we're just grabbing all the tuples. Maybe a more sensible thing might be that we do a filter, so we're creating a subset of some relation as a new relation. Right, so effectively what's going on here is that we're copying data from one file to another. Now, it may turn out that the copied data file has less pages than the original data file, because maybe we've got partially full pages here, and if we're dealing with a heap data structure, then we can pack tuples in and make sure that every page is full. So in this case, pages might not necessarily be full. In this case, they're guaranteed to be full except for the last page. So that's one aspect of that. So how does that boil down to operations on files? Right, so clearly we need to open the files for the two relation. Let's assume that we don't have forks and we don't have overflow pages and so on. So we open the relation S for reading, we open the relation T for creating and writing, and we have an output buffer. So in this case we need two buffers. We need an input buffer to read pages from the relation S, and we need an output buffer to build up pages for the relation T. So we iterate through all of the pages in the input file. So we can get a page number, so we say let's read in the next page in the input file, store it in the input buffer, and then scan through the input buffer and get the next tuple in the input buffer and add it to the output buffer. So we can keep doing that, and we may read multiple pages from the input file before we eventually fill up the output buffer, but when we do, we have to write the output buffer to output. So we don't necessarily say, right, reading page 0 of the input file, scan through all the tuples, write out page 0 of the output file. We wait until the output buffer is full, then we write it out. And then we increment the output page number and so on and so on. Now, of course, when we get to the end here, we might have some partially full output buffer. So we have to make sure that we write that out if there are some tuples sitting in the output buffer. And this kind of strategy crops up quite frequently in practice. Alright, so how much is it going to cost if both the input and the output are heap files? Well, let's go back and have a look at this. That's reasonably straightforward. Clearly we have to read the input file, all the pages of the input file, and then we have to write all of the pages, possibly less pages, to the output file, so it would be B in plus B out. Okay. B in reads plus B out writes. If the input file is sorted and the output is a heap file, doesn't matter, same cost. So we just read the sorted file, we happen to get the tuples in order, and we dump them in the output file. So we have to read the entire input file and we stack it into the output file and write it out. So B in plus B out. If the input file is a heap file and the output file is a sorted file, that's slightly more interesting. The naive way to do it would be to say, effectively, get the next tuple from the input file and then insert it into the output file. So the output file doesn't build up page at a time like that. It builds up by us actually inserting. So we can't save an output buffer in memory. So in fact, we kind of lost the output buffer, and what we end up doing is an insert for every input tuple. Now that's clearly going to be expensive because every insert operation in this case involves finding the appropriate page, writing that page, or modifying that page, writing it out, and potentially pushing stuff up. If the input was sorted, then that would be simple. It would just be this case here, basically. Now, another option, if the input file happens to be small enough, just read the whole thing into memory, do a sort in memory, and write the tuples out. So that would be the sneaky way to do it, but it relies on you having enough memory to hold the entire input relation.
So, like when copying, the input buffer and the output buffer are different?
Yeah, clearly.
And how is the size of the buffer defined for the input and the output?
Oh, both the same. Well, in fact, it doesn't. It doesn't matter. But the size of the buffer will typically be determined by whatever page size the DBMS is using. So we're talking about each of these buffers represents a single page from a file. Okay, and generally, in Postgres it's always 8K. But I mean, you're right, to some extent it doesn't matter how big the output buffer is, we'll just be writing the output in smaller chunks if it happens to be smaller. But the typical assumption is all of these buffers are going to be the same size and they're going to live in the buffer pool. In this case, we're not getting any help from the buffer pool at all, unless someone just happened to have read the information from table S at some point in the recent past. Right, so here's an interesting one. So multi-value concurrency control. So we've talked about getting a tuple as basically just going to a page, looking at the ith entry in the directory. That tells us whereabouts in the within the page the data for the tuple lies, and we go and fetch that data. In this case, if we ask to get the ith tuple from a page, it's possible that that tuple no longer exists as far as this transaction is concerned. The tuple's still sitting in the page, it's got a directory entry, but in theory we can't see it because it was deleted before our transaction started. Alright, so we assume we got multiple concurrent transactions. If we don't, then this problem isn't that interesting. So how do we know that a tuple is visible to us? Alright, so I think I've actually got left out an I, did it? Alright, so visibility of tuples to a transaction in Postgres determined by two things. It's certainly determined by the transaction, but a transaction can consist of a number of different commands. And if one command early on in the sequence of commands is doing an insertion, then later commands should be able to see the tuples there. But if we're looking through the table in an early command and a later command does the insertion, then we shouldn't be able to see the tuple that gets inserted later on. Now clearly, if we've got a tuple that was deleted by a transaction that ran yesterday, then that tuple's gone and we won't be able to see it either. So each transaction that runs in Postgres is allocated a unique ID. The IDs are allocated sequentially, so you guarantee that if you've got a higher transaction ID, then you're running later than a transaction that's got a lower transaction ID. So a transaction is a sequence of commands, where a command is a single SQL statement like a select or a delete or an update or an insert. Each command has an ID that's unique within the current transaction. So each tuple contains all of these things. Now CTID is not really relevant for this task. So each command within a transaction knows what transaction is currently running in, and it also knows what its command ID is. Okay, so how do we work out whether a tuple is visible or whether it's live, if you want to put it like that? Alright, so if our transaction ID is later than xmin, then the tuple was created before we started execution. That's a good start to make it visible. And also, if it hasn't been deleted yet, which is what this second test is, then definitely it's going to be visible. Okay? So, must have been created before we started and must not have been deleted. So you could have something that was created 5 days ago and deleted 3 days ago, so that kind of tuple wouldn't be visible. If you're talking about within the transaction, so if it turns out that the xmin value is the current transaction, then we've got to worry about whether some earlier command inserted the tuple or whether it's going to be inserted later on. So as long as the CMIN value, as long as the command that inserted the tuple runs before us, then the tuple is also visible. It's an interesting question as to whether the tuple would even exist if it's created by a later command. But anyway, that's certainly guaranteed to make the tuple visible. Unless it was deleted by a subsequent command. So we've got a transaction that says insert tuple x, delete tuple, and this is a pretty weird transaction, but insert tuple x, delete tuple x, and then do a select on the table. Okay. So the select shouldn't see the tuple that was deleted, and it's not going to see it if the x max value the C max value, so the x max is basically the current transaction. As long as the C max value is greater than the current command, then we can see it. And yes, you're going to say, how could that be?
I was going to ask, in theory, couldn't you have an x max value that's higher than your current transaction?
Yeah, but all right. Okay, we're not applying these independently, but that would get filtered out by this. Oh, sorry, it wouldn't. Yeah, you could. Yeah, if you got an x max value that's higher than the current transaction, that's fine. It doesn't. It means that it hasn't been deleted yet. It's going to be deleted in the future. Interesting how these values actually get set. Yeah.
I'm just wondering, do these transaction IDs live in the database forever and just keep increasing? Do they get reset?
They could.
Just wondering.
I said, yeah, I know, because I said that they're continually increasing, right?
Right, so if it's 30.
Yeah, I have a feeling there's also a timestamp floating around in the background somewhere.
Right.
So you know whether it was before this one.
It's just thinking with only 32 bits, we could easily wrap around.
Yeah, sure. Yeah, I agree.
What if there are several transactions interleaving?
Yeah, sure.
Yeah. Then what is x mean?
X min is the transaction that created.
Like before those transactions commit.
Yeah.
Then what is the value of the?
Oh, all right.
Yeah.
The value of x min.
The transaction hasn't.
Yeah, sure. It probably has no value. I think it doesn't exist until you commit. So there's no x min. These fine details. I would guess that it wouldn't make sense to have an x min value for a tuple unless the transaction had committed, therefore the tuple exists. Yeah, it does your heading, transactional stuff. And multi-version concurrency control. I'm going to stop on that one. Anyway, you can go away and have a think about that. It's turning into a mess. And it's almost 2 o'clock, so let's run away. And next time we come back, what will I start talking about? Oh, yeah. So what does scanning look like in Postgres? So, I assume there's this abstract scan structure. Postgres obviously has something like it. And strangely, it's called heap scan descriptor. So it contains the state like what's the current page, All right, I'll stop there.